Well, hello everyone, welcome back to Adrian's Digital Basement 2. On today's video, it's just a quick one, hopefully quick, on repairing this Commodore 128 motherboard. What I want to demonstrate in this video is that there are times when you might have a Commodore 64 or a Commodore 128 like this, that mostly works, but then has a fault, and I want to demonstrate how to fix that without actually needing to have, well, any test equipment at all. I'm not going to use oscilloscope. I'm not going to use the cartridge that plugs in here, or the test harness, or any of that stuff that you may not have if you just have one of these machines and it's exhibiting a fault. Of course, this diagnosis that I'm about to do is highly dependent on the type of fault the machine has, but the fault that this thing has is pretty common and is something that could happen all the time. And really, this is just an example of a fault that I wanted to be able to show off that you can actually fix with just using, again, like I always say, your eyes, your senses, and a little bit of thought. Let's plug this thing in and let's see what it's doing. Now, this Commodore 128 motherboard is actually one of my spares. It doesn't have a case to go with it. I don't have the keyboard or anything. My working 128, well, it's funny, this was in my 128. I went to use it and it has the fault that we're about to see this thing has. So I just swapped this out with another spare motherboard that was quicker than me doing a repair. So right now, this repair is going to be done without the keyboard even. So I can't fully test this, but to be honest, I should be able to put a cartridge in there and play a demo or whatever. Oh, this thing has no SID either, so it's going to have no music. I took the SID off this and moved it onto the other motherboard. This motherboard obviously has stuff going on here. I think this is stuff that I've done personally because I vaguely recall doing this mod. The thing that's over here, I don't even know what this stuff is, to be honest. What is this? Copyright Commodore. Is this an actual aftermarket ROM? I think it is. I don't know. And I think this was obviously it's a kernel switching thing of some kind. It's connected to the motherboard right here. It also connects to the motherboard through this green wire. If we zoom out here, over here, I don't know. I don't remember what this is. There's obviously a component installed under here. Must have been something that someone sent in, and I just don't remember what it is. This is what happens when I do stuff that was done a long time ago. What is this? This must have been repaired. This wasn't a repair. That must have been something that Commodore did. But this, I don't know. No, there's glue on here. This had to have been something that was done in the factory. I don't know. I don't remember doing this. Not me personally. Now, every 128 has this wire installed on it. And so the glue on here looks similar to the wire that's underneath, but every single one has this. It goes from that chip over here to the Z80 CPU. Some kind of fix. I'm sure Bill Hurd, if he watches this, he can chime in on the fault here that required them to put this wire in here. Now, the wires on the back, I don't remember seeing those, but you know what? I don't work on many 128s. These are pretty reliable machines, but like I said, this one's got a fault. So let's plug this in here, and I want to demonstrate the fault, and we're going to fix it without any test equipment, as I mentioned already. Okay. All right, so I'm connected here to the RetroTink, and we turn this on. And come on. There it is. All right. Well, we can see that the computer has seemingly crashed. It says red without the rest of the ready prompt, and we got some flashing zeros on screen. Now we hit the reset button, and you can still see flashing. In fact, it's worse now. The computer's not even coming out of reset. Here's the thing. Oh, there we go. We got a ready prompt, but we have zeros all over the screen. All right. So what do you think is wrong here with the zeros? If you have watched a bunch of my videos, you probably have a good idea. Let's talk architecturally about the way that the C128 and also the Commodore 64 works, because they're very similar, at least in the regard of what's happening here. The display on the Commodore computer, 64 and the 128, is generated by the VIC chip. I guess the VIC-20 is very similar as well. What's happening on this machine, the VIC-2E, which is this 48-pin DIP here, works in a very similar fashion to the VIC-2 on the 64. It uses part of RAM as its display buffer for the text mode. And what we're looking at here is text mode. Now, there are graphics modes, bitmap graphics modes, and things like that also work. But what happens when you first power on the machine, the OS is initializing the system, and it just sets this up in text mode. And that means that one memory location in RAM is a character on screen. Now there's also a color RAM. It's a separate little piece of memory, SRAM, static RAM, and it's mapped to a different location in the 6502's memory map, and that handles the color of each character. So if you turn on your system and everything looks good from a text mode perspective, but you have random colors around the screen, then there's a possibility that you have a problem specifically with the color RAM. The color RAM is not part of the main memory. And on this machine, there are 2 banks of 64K. What's held in there is, like I said, just the text mode and the bitmap stuff, but the color is held separately. So what's happening in the case of this machine is that the background should be solid gray, but what we're seeing is spurious zeros instead. Now, when we turn the computer off and on, obviously it's acting a little funny as well. Okay, I/O error, I mean, all sorts of weird things are happening. But what is obviously going on here is, remember that the memory locations in RAM are what hold the characters. And obviously we have failing memory on this machine, so that it's doing a couple things. As the video chip goes to read out the screen buffer to display it to the screen, it's, instead of getting all spaces, which is what the CPU would have written into the RAM, it's reading back zeros. But we're also getting this random crashing, and I'm pushing the reset button here, and there we go, it didn't crash that time. What's happening with the random crashing is that whatever memory problem we're having here is affecting parts of the RAM that are used for the operation of the computer. Parts of the RAM is dedicated as a stack, where it stores temporary values, it pushes them on and off. There's a 0 page where there's a bunch of variables used for the operation of basically in the operating system in the case of this machine. And if there are any spurious memory errors in that location, especially ones that kind of come and go, and remember a little while ago we had a 0 that was kind of flashing off and on, that meant that that memory location was kind of working, kind of failing. And if that's happening inside those 0 page or stack area, then that can cause random crashing of the system. Let's do the reset again here and just see. Yeah, I mean, look there, it just totally was unhappy. But even when I hold down the reset button, where there should be all spaces, which is a kind of a weird garbage character right now, while the character ROM is not in effect, there are obviously memory locations there that, don't follow the same pattern. And I think that is that exact same problem. It's that RAM thing. I'm going to turn the machine off, turn it back on. Okay, well, now it's totally crashed. So it's maybe degrading. I don't know. It's quite possible it's getting worse, whatever RAM problem is happening here. Okay, yeah, the computer doesn't even appear to work at all now. All right, so it's cool that the problem on this particular machine is not just a black screen. If the RAM problem became bad enough, then we would end up just with a black screen. The system will not run without a functional 0 page, a functional stack. Those things are necessary for the system to work. So this memory error, which if we look at the zeros, there aren't that many in the entire screen buffer there, which means they're probably interspersed around the rest of the memory as well on the system, but it's not enough to keep the computer from running most of the time. In addition, notice it's counting up RAM there, 122,365 bytes free. This is running, of course, in Commodore 128 mode, and it's able to use both banks of memory. So we're not just limited to the first bank. And on the 64, of course, the BASIC on there, the old version of BASIC, the BASIC version 2, isn't even able to use the parts of the RAM that are under the ROM. Now on this machine, there's a memory management unit that actually handles the banking of memory, and it's more sophisticated than on the 64. In fact, the Commodore 128 can actually support up to 256K of memory right on the motherboard. Now there's no provision for that RAM to be installed, but the memory management unit on here does support up to 4 banks of memory. Currently there's only 2 banks of memory, and depending on the configuration of the MMU, you can have the ROMs mapped in there, part of the RAM, you can have bank 1, bank 0. But one thing with the memory management unit on this is that the first 400 hex bytes of memory, I don't remember what the number is in decimal, but from location 0 hex to 3FF hex is always in bank 0 of RAM. As far as I'm aware, you can't access that first little chunk of RAM in the second bank. I'm going to try to draw this out on a piece of paper here just so we can see it a little more easily. So if we imagine this is the memory space, and there's 2 banks of memory. So I'm going to put bank 0, and we have bank 1, which is from 0 to FFFF. what happens is there's a little chunk of bank 0 here that goes from 0 and it goes to 400 hex. Oh wow, this is really difficult to read. And no matter which bank you have selected, if you select bank 1, you're actually always going to have access to this first 400 bytes. This little chunk right here is always going to be mapped in from the bank 0. Now what's happening on this computer, besides we see these random zeros sprinkled around, and generally the screen buffer is in the first little bit of memory here from 400 to, I don't remember the top part of the address, but that first chunk of RAM after this reserved area with the stack in the 0 page, that's 400. I wish I wrote that a little more clearly. Let me grab another pen. So I stopped drawing with the Sharpie there. So this is 400H. Wow, that's not easy to read, is it? So yeah, 0H to 400H. The screen buffer starts at 400H and it goes down to, I don't know what it is, like just I don't remember what it is, but I'm just gonna say like 800. So imagine there's that much that's used for the text mode. So here's the thing on the 128, there are 2 banks available to us, right? And when you switch over to bank 1, remember I told you that first chunk of memory is always mapped into bank 0. It's always coming from the RAM, the physical RAM in bank 0. But the rest of the memory from here all the way down to there is actually coming from the second 128K, and that includes the screen buffer. Now the VIC2 allows you to move that screen buffer anywhere in memory as well. It can be over here, or it can be all over the place. And when you switch over to bank 1, the VIC2 can access the memory for drawing the screen from the second bank of memory as well. So I don't know with C128 Basic, when it first initializes, if it leaves the screen in this normal area, 400 to 800 or 400 to whatever it goes up to, or if it moves it. It's probably in this stock area, and that means you can poke in to memory locations to actually put a character on the screen. But I don't know which of the banks it's in. That's the thing I'm not sure about. And I'm assuming when you just use regular poke commands, you only have from 0 to 65535, which is FFFF, to poke into. And if you're going to access the other bank of memory, you must have to do something with the MMU to switch over to it, and then you can poke into those memory locations. So I'm assuming with these 128 Basic, it leaves us in bank 0 when it's just sitting there, and it leaves the screen in that first location. Now the reason why I'm talking about all this is we have to figure out which of the RAM chips is bad. And because this machine has, well, let me move it over here. It's got 2 sets of RAM chips here. Well, one of these is bank 0, and I'm pretty sure it's this lower row of chips. And then there's another row up here, which is the bank 1. And if we figure out that, say, one of the RAM chips is bad, we have to kind of guess which one it is. Because if the screen memory is sitting there idle and it's reading from bank 0, and we change out one of these RAM chips up here in bank 1, that's actually going to have no real effect. Now, you can notice by looking at this that, well, we got empty RAM here. And it goes without saying that empty RAM is garbage. And at this point, these go bad. And I've already replaced, or someone's replaced, 2 RAM chips on here already. I don't remember if it was me or not. But we obviously have another bad RAM chip. Now, one thing that would be possible is we could just remove all of this RAM, except for the 2 that are already swapped out, and just swap everything else out. But let's make an assumption here that we don't want to do that because maybe we have a more rare type of DRAM, or it's not empty RAM, you don't think it's all bad. Because regular RAM goes bad too. It's not just empty RAM that goes bad. It's just empty RAM seems to go bad at a much higher rate. So I wouldn't say you're doing a bad thing by just swapping all of the empty RAM out, because ultimately 2 chips have already gone bad on here, or whatever. Someone already swapped out 2 chips, and yet we have another bad RAM chip. I know this motherboard was working last time I used it, which was a while ago, so one of these chips has failed since then. But if it was a different brand of RAM, well, there's a good chance that the rest of the chips are going to be fine and work forever, and one of them just failed for whatever reason. So let's just imagine that we're not dealing with empty RAM, and let's figure out which of the chips is the candidate for causing those spurious zeros on screen and also causing our random crashes. Okay, so now the question is, how do we figure out, well, which is the candidate bad chip? It's actually really, really easy. All we're going to need to do is take a look at this, the Commodore 64 Programmer's Reference Manual. Now this book's available online. You can find a copy of it, or if you have one of these machines, you might actually have one of these. Let's look inside of this and figure out exactly what's wrong. We can use this book to help us identify exactly what RAM chip is bad. And while this is for the Commodore 64, it doesn't matter, because what I want to look up is I need to find in here this right here. It's funny, I just sort of opened the book right to it. Sometimes it's far easier to actually have the book than a PDF, because when you're trying to search through a PDF, you know, when there's so many pages as this, it can be a little bit difficult. We are looking specifically for the screen display codes. So what the screen display codes are is, remember how I mentioned that the characters in text mode are stored in RAM as some kind of a value, and then when they're displayed by the VIC chip, it reads the RAM, that location of memory, and then it goes and looks up in the character ROM, or whatever font it's using, what should be displayed on screen. Now, the values for screen code, what's actually stored in RAM, is not the same as what's in BASIC. When you're using BASIC and you like print CHR $, and you put a number there, that's not really always the same. It can often be similar, but the BASIC stuff is actually written to be compatible with ASCII, because it's Microsoft BASIC, right? It needs to be compatible, again, across all the different computers, like the PC and Apples and stuff like that. But PETSCII, which is the font that's being used on the 64, actually is not really ASCII. It's PETSCII, it's different. And the characters can map into different locations. So on some computers, the character set in the display driver maps directly to ASCII. So if you store in memory a particular value, say 64, then what's displayed on screen is going to be exactly the same. You put 64 in memory and you're going to get the character you expect. But on the Apple II and on the Commodores, that's just not the case. The fonts don't match ASCII. So when you print a space or a 0, remember we're seeing zeros on this machine instead of a space, you cannot just assume that the value stored in RAM is actually the same as the ASCII codes. Now, if you know Commodores, you know that there are two different character sets, and one is lowercase, so like there's C and lowercase c, but in the default configuration when you first power up the computer, we're in the uppercase character set, so we're looking for set 1. And then the poke here is the actual value of that character stored in RAM. So on Commodores, when you store a value of 1 into the RAM, it's displayed as the letter A. And that's where ASCII and PETSCII diverge a lot, because the ASCII value for A is not 1, it's something much higher up. I forgot what it is, but all the first bunch of characters in ASCII are just blank, because those are control characters. So the A value is like, 20 hex or 25 hex or something like that. It's further up there. So you always have to understand first how the display hardware works and what the character set being used is for the computer you're using, and how those characters, which you're seeing on screen, which are problematic here, map back to particular RAM bits. And that's what we're trying to do here. The screen should be filled entirely with the letter space. Obviously not where the text is written at the top, but further down in the blank area, anywhere there's just nothing on the screen, it's space. And that value is 32, and this is going to be in decimal. So I'll just write a D there so we know that that's decimal. What were we seeing instead in those few spurious characters? We were seeing zeros. And that, well, I'll just put space here so we know that's a space, and we end up seeing a 0. And a 0 in PETSCII is 48. And again, remember, this is in decimal. So to restate it, what's happening on this computer is when you power it on, you get the banner, and then the kernel tries to fill the entire screen buffer up with spaces, because there's going to be garbage in there when you first power on the computer. So it fills it up with spaces. So it writes 32 decimal to everything. It'd be the equivalent of just poking this value into the whole buffer. But then when the VIC goes to read it back, instead of reading space in all those character cells, which is 32 decimal, in some of them, it's reading 48. So when it writes 32 decimal, if we convert that to binary, so I'm going to write that 32 is 00100000. And remember, this is the least significant bit. So that's data bit 0, so like D0. Oh, this pen's acting up. So that's D0. And this right here is the most significant bit. The top one here is D7. Oh, I wrote P. D7. And luckily, the way Commodore wired up the VIC chip, yeah, they wired up the chip on the motherboard that is representing data bit 0. If you look at the schematics, that goes to the VIC chip along with all the other ones. And when you have all zeros, and except for data bit 5, you have that as a 1, you end up with a space character displayed. All right, so when we have 48 displayed, what that converts to in binary is 001100. 0, 0, 0, 0. So right there, we know immediately, and I wrote the wrong thing there, we know the problem is data bit 4. So remember, 0, 1, 2, 3, 4, 5, 6, 7. So this one, which was written as a 0 by the system, by the kernel, when it's read back by the VIC, in some of those locations, this data bit right here is the problem. Now I skipped over that conversion to binary, but you just use any kind of programmer's calculator like the Windows calculator. I assume on Macs you can do it too. And this particular book is displaying these poke values. And remember, with pokes in BASIC, you are just using from 0 to 255. So you're using decimal as opposed to hexadecimal. So you just need to make sure you got your numbers right, because if I had put in 32 hexadecimal and that turned into 48 hexadecimal, we would have been looking at the wrong bit. So you need to remember it's decimal, and then we converted that to binary. Okay, so we're done with this book. We know for sure that it's data bit 4, that's the problem. Now in here, if you're using it for Commodore 64, there is a copy of the schematics and stuff in here, but since we're using a 128, I think there's maybe an equivalent book for the 128. We're just gonna go to Zimmer's and find the schematics to figure out which chip is data bit 4, which we have identified as the bad chip. All right, if you go to zimmers.net and you go to C128 under schematics, there are various pages. Here is page 4 that we're interested in. Here is page 4, and you can see all of the RAM chips right here. And what we need to do is zoom in a little bit, and we'll figure out exactly which is the data bit that's relevant. 0, 1, 2, 3, and we scroll over a little bit. There it is, data bit 4. Now I'm just gonna write down on my piece of paper here, it's U42. There it is right there, U42. But we also have to look at this one down here, U50. And that's because one of these is bank 0 and one is bank 1. And I'm not sure which is which. Now when we scroll over here and we take a look at the signaling that goes to the RAM, RAM uses a RAS and a CAS line. That's row address select, column address select. The RAS line is actually connected to all of the RAM chips. You see RAS goes through here to pin 4, and it also is connected down here to pin 4. So the RAS line is common between all of the RAM chips on the motherboard, but it is the CAS line that is separated. So here we have RAM CAS 0, and that goes through to all of the CAS lines on this top row of chips, on the schematic that is, U38 and up. And then down on this other bank of RAM, 15 here, if you follow this up, is RAM CAS 1. So I'm assuming this GCAS 0 and GCAS 1, this must come from the memory management unit, and it allows the system to select which of the banks of memory this is. And there are probably extra GCAS lines for the other two banks of memory that aren't implemented on this thing. I think they come out of the memory management unit and the circuitry is missing to support that extra memory. But theoretically, it could be bodged into the system here if those signals are there on the MMU. I've never looked into it. In fact, today I just did reading about how the memory layout works on the 128, and that's when I read that it supports 256K. Anyhow, let's just make the assumption that RAM CAS 0 is bank 0, the one that's used when the system starts up, and that RAM CAS 1 is that upper amount of memory. And specifically, I wrote down U42 on the paper here as the bank 0 chip there. There it is, U42, data line 4. So I think that's bank 0, data line 4. And on the motherboard right here, we're looking for a U42. That would be this chip right here. So I'm just gonna grab a marker and put a mark on there. So I think that that's our bad chip right here. Now it could well be this chip up here, which is U50, right? That was the other bank that I wrote down. I don't know. Someone obviously swapped these two chips out in the past. I don't think that was me because, you know, I like to use those round hole sockets, but we're still gonna go off the assumption that it's this chip right here. Now, when we looked at the bad bit, the 0 changed into a 1. Now that's actually an interesting thing. I'm sure you've heard of the piggyback method to try to identify if a chip is bad. Well, with a bad chip like this, we know the chip is mostly working, right? Like most of the screen has the correct text on it. There's only a couple characters, or well, it was like 5 or 6 that are bad. And we can imagine that's sprinkled throughout the rest of the memory as well. Well, here's the thing. We know the chip is outputting a 1 when it should be outputting a 0. Well, here's the thing about doing the piggyback method. When I put another RAM chip on there, all the inputs to the RAM chips are the same. The one I'm holding on top and the one that's already on the motherboard. It's the output drivers that are going to be conflicting with each other. Well, the chip on the board is going to be outputting a 1 or something like a 1, but the chip I'm holding down, if it's a good chip, is going to try to output a 0. So that actually creates a bus conflict on that signal when it's reading that particular memory location. Most of the other memory locations are working on the chip on the motherboard, and therefore there will be no conflict. Both chips will be driving the bus to like 0 or 1, you know, at the time they're supposed to be doing that. But when there's a conflict is where, well, doing the piggyback method can or may not work. Well, here's the thing. TTL logic can pull down to ground really strongly. It can sink a lot more current pulling to ground than pulling up to 5 volts. Well, that's a good thing because it seems that this bad chip is pulling up to 5 volts when it shouldn't. So putting a chip on there, a piggyback chip, should be able to override that 1 value that's coming out of that chip when it shouldn't and force it down to ground. And theoretically, putting a new chip on that one location should get rid of all those zeros. Let's give that a try. All right, so I have another empty RAM chip, but I have one that I have a tick mark on, like I've tested, and it works. And we're gonna use this to do the piggyback. So all I need to do is make sure all the pins are straight, and they are. And I'm going to push this down onto the other chip, like that. I'm just gonna hold my finger on it. I'm going to turn on the system. We're getting nothing. I pushed the reset button a few times. Okay, that did absolutely nothing there. Interesting. So maybe it is the other chip, the top one. So I'm gonna pull this off, and yep, the computer didn't crash, it didn't do anything. So I'm gonna push this down onto the top chip there now, U50, and let's turn this on. That certainly looks different, doesn't it? And I think what's happening here is the chips are fighting right now. And that's sort of, that's actually causing some issues here. It's hard to even get this computer to start properly. Well, okay, maybe not. I'm gonna try another chip, a non-MT RAM chip. All right, I'm down on U42 now. Again, I have a different brand chip. All right, that doesn't seem to do anything at all. Pull it off, no change. Okay, I'm on U50 now. Let's see if this does anything here. No, no, nothing. Oh, I just realized what I did wrong. The RAM chips are installed, well, all the chips on the motherboard are installed with the notch facing me. I had the chips in upside down. I might have damaged both of these. Let's do the piggyback again. Let's do it the right way. How about that? Yeah, I'm pretty positive I had the notch facing away from me, and the notch is very clearly facing towards me on this system. Oh yes, there we go. If we pull the chip off, the zeros show up again. Yes, 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 yes. So piggyback method works when you put the chip on the right freaking way. All right, well, I've identified for sure the screen memory when you're sitting here in C128 Basic uses the bottom row of chips, so that's a good thing. Let's power cycle the computer and see if we get more of those zeros back. It'd be kind of hilarious if piggybacking this kind of fixed that chip a little bit. We definitely had more zeros on there than we do now, although the flashing zeros are pretty hilarious. Let's just piggyback the chip one more time. Okay, it's on there. There it is, working perfectly. Nice, 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 nice. Okay, and I was moving the chip around there and it was unhappy. All right, well anyways, there we go. Problem is solved and looks like the chip is spontaneously failing worse now. All right, so I've identified for sure this is the bad chip, but here's the problem. What if you don't have a good way to desolder a chip in a way that's safe and not going to damage the board? Well, there are ways around that. And what we can do is we can actually just solder this chip directly onto the pins that are left behind there. Now with a 4164 DRAM chip, what happens with the MT chips when they go bad is the memory cells on them just stop working properly. They don't fail like short or having other weird problems. The issue is what is being output from the chip is just not working properly. Well, everything on a 4164 is an input except for these two pins, 14 and 2. So all we need to do really is cut those 2 pins on the chip on the motherboard and then just solder this new RAM chip right on top of the old one, and that'll fix the problem. Cutting the 2 output drivers on the 4164 eliminates the bus conflict that putting this on top of the other chip is creating. Anytime the bad chip is reading a 1 and this is trying to read a 0, you know, that is the bus conflict. And yes, this chip wins, and that's why we were getting, you know, a properly operating system. But the reality is you shouldn't leave a bus conflict, you know, in the system. So I'm going to cut pins 14 and pins 2, and then we'll do this little soldering experiment. I've never personally done this type of repair before, but I think this is a much safer way to replace a chip if you're not sure about how to desolder stuff in a way that's safe and won't damage the machine. All right, so looking at this chip here, that's pin 1 right here. Now there's a dot there on this RAM chip that signifies pin 1, or say on this one, if you're not sure when the notch is, it's always pin 1 right there. So we know it's pin 2 as the output. So I'm going to try to cut this. My cutters aren't the best here. They're kind of damaged. They didn't really work so well. It did cut the pin, but now the pin's all flopped over to the side. So down here at the bottom is pin 8, 9, 10, 11, 12, 13, 14. So this is pin 14 right here. And hopefully you can see the issue with my cutters. The tip is busted off, half of it. Oh no, I just realized I cut the wrong pin on the wrong chip. Oh dear. All right, we'll fix that in a second. Okay, there, I cut it off the right chip there. I'm just gonna cut this one more time here. So those pins are cut. I know it's hard to see, but it's definitely not touching on this side, and it's not touching on that side. And then with this one, I cut that pin so close to the body that it's actually disconnected now. You know what? Let's just try to fix it. So what I'm gonna do is I'm gonna use this tool here. I'm gonna try to bend that pin and have it touch the body of the chip. And while I'm at it, I'm just gonna use my little engraving tool here to try to I'm gonna try to expose some more of the metal in the body of the chip there. I think that worked. I think that's gonna work. I just use a little engraving tool here. I'm just gonna put a drop of flux there, and I might as well put flux on all these pins here. And I'm just gonna try to solder this and fix it. I don't know, that might be okay right there. Hopefully. Okay, so for the chip that I'm gonna put on top of the other one, I just need to bend out pins 14 and 2 a little bit because I need them to clear the cut pins. And I'm just gonna push this down onto there. I think that's making good contact. And here we go. And I'm gonna hold it down with one finger and I'm going to try to just solder the pins right onto here. I'll do the corners first. And I am just going to try to get all the pins connected up. Now it goes without saying that normally I would never do this. You know, I would just, I would remove the old chip, put a socket in. But let's be honest, not everyone is able to do that very easily. And you know what? Worst case, I just remove all of this mess I make here and I, you know, solder the chip in to a socket. But I think this is going to do the trick. As long as I don't short things together here. And I make sure that every pin is making contact with the chip underneath, I think this is gonna work. All right, so I have half of the chip done, right? Let's turn this on its side here so you can just sort of see what I'm doing here. See that? There you go, that's what I mean. So it's attached. It's sketchy, but it's attached. All right, so I can tell that I've created like a solder bridge over here in this area. Didn't do a great job. So I'm gonna use some of this wick here to try to clean up the mess I made. Yeah, that worked. Cool. Okay, there we go. It looks a bit ugly, but I think everything is connected there. This is where having a multimeter will help. Put this in continuity mode. And then what you can do is you can just test all the pins here. So for instance, this pin here will be connected to this pin here, and so on and so forth. All of them except for 2 and 4. So we go down the row, make sure everything is connected. It is. So pin 2 is not connected to this chip over here, but that's expected. It will be connected to this chip here, so that's good. All right, so now this pin here. Huh. Okay, wait a second, they're not connected on any of them. Oh, that's right, that pin is just not connected. That is used on the 256K chips, but not these. So that pin 1 doesn't go anywhere. Okay, sorry, that was my bad there. Moving on. Okay, so that's this pin. That's connected. Go over here. Okay, everything's connected, including the 2 pins, pin 2, which would go up here, and pin 14, which goes there. Nice. And then the one here that I massacred, pretty sure it's connected. Yeah, I mean, I don't know. We'll see when we turn this on what happens exactly. But I think this should work. Power and video's connected. Turn this on. It's freaking working. Look at that. Yes, so that means that the damage I caused to the wrong chip wasn't a problem, and then the new chip is working. Now, if the chip that was gone bad had like gone short or something, it could bring down the address lines and all that stuff. You'd really need to remove the chip. And in that case, what you would do is cut the entire chip out and use your soldering iron and tweezers and one by one just pull out the pins. It's very easy to do that. You won't damage your board. And then you got to use something like the solder braid here or a solder sucker to just clean out those holes. And then you could properly install a socket and then a new chip. But this method here really does work. I know it's sketchy and sus, but it's working. It did the trick and there was no damage caused to the motherboard at all. I know the way I attached the chip here, people are gonna cringe at that. But look, I have fixed many damaged 64 and other computers where people had attempted to remove bad RAM chips and they destroyed the motherboard in the process. In fact, the back of this has a bodge wire right here because whoever put those 2 sockets in, they damaged this motherboard in the process. So that's a perfect example. And when you damage your motherboard with a trace that you lift by pulling a chip out, then when you get it all back together, you're just gonna get a black screen. So you'd go from a machine like this that was mostly working with, you know, some bad characters to something that's totally dead. So it definitely takes extra troubleshooting skills to be able to identify a bad ripped trace and then repair it with a bodge wire, which is clearly what happened with one of these 2 chips here. So that's why this method, as sketchy as it is, it totally works. And as long as you disconnect the output of the original chip, you can leave the rest of the chip in there and it's totally fine. But as I said, like the better way to do it would be to cut the entire body off and then pull the pins out one by one and then put a socket in and then put a chip in there. Because now obviously if this chip goes bad, well, you know, I could take it out, but it would be a much more difficult task. Although with a desoldering iron or just cutting off the whole thing, you know, again, cutting the whole body off, both chips, and pulling the legs out one by one would still be totally easy. But yeah, someone's obviously had to do a repair on this thing there. And this method is a surefire way to get a new RAM chip in there without causing any issues. Now in this case, the Piggyback method actually did tell us which chip was right. I mean, I put those 2 RAM chips in the wrong way, so that didn't work at first, but once I got that right, then it worked. We had identified for sure which bit was wrong based on the characters we were seeing on screen. We didn't need any special test equipment, we didn't need a special cartridge, we didn't need any of that. We just needed the book, which you could find online, and a little bit of logic and a calculator. And we were able to get to the bottom of exactly which chip was wrong. And I guess the only thing I didn't know is if it was the top chip or the bottom chip, and the Piggyback method is what helped us there. Worst case scenario, I would have put a chip in here, like with this method, it wouldn't have fixed it, and then I guess it would have been the other one. What we can do is put in this cartridge here, which is a 64 cartridge, And we'll see, it should load 64 mode. Oh, there we go. I pushed reset a few times. I don't know what's going on. Maybe there's another fault on this machine or something, but clearly the system is booting up there. Let's try that again. Yeah, okay, there we go. And I don't have the keyboard, but I plugged a controller in and we should be able to control things here. So I think I have diagnostics on here. I don't think I can run 128 diagnostics on here, but let's just try this one here, just to make sure that first bank of memory is all working correctly now. Obviously, I could have run this earlier. I'm not sure this would have even worked, but I could have run one of the other diagnostic cartridges. But the whole point was here, it was to do this without any cartridges, because not everyone has cartridges, and sometimes you want to just fix your system, and this is one way to do it. Now, when you're looking for replacement chips, by the way, 4164s, these are the DRAMs that you need for fixing these things. You can also use 41256s. They have the same footprint, and other than that extra pin 1 that's not used on these chips, you can completely replace the chips that are on here with the 256K chips. You don't get the extra capacity. They'll just work as 64K chips. But if it's easier to find those, then you can totally do that. Checking here, RAM test 1, 2, all good, all working. Okay, so first bank of memory is fully functional. That's this bottom row is totally good on this 64. What we can see is that the system is totally working. And if you run Adrian's tools, we can do the 8-bit dance party. Let's try the top here. Graphics are working. I mean, it would not work at all with that bad chip in there, the original bad chip. It would be totally dead. This, on the other hand, is working great. So there we go. Repair the system with some cutters, a soldering iron, a new RAM chip, some solder, a little flux, and we got this system up and running again. That's what I wanted to show. And yeah, so put your comments down below. I'm waiting for that criticism. I'm sure lots of people are going to be like, that was horrible. But you know what? I just wanted to demonstrate that it is possible to do it with no damage and be safe about your repairs. So there we go. If you liked it, thumbs up. If you didn't, you know what to do. Subscribe, all the usual YouTube junk. Thanks from patrons. Names are going up the side of the screen. Stay tuned for a little bonus footage. I'm going to test these 2 RAM chips in just a moment. So yeah, that's going to be it. So stay healthy, stay safe, and I'll see you next time. Okay, so for testing this RAM, I'm going to use this tester here. It's USB powered. This one here tests 4116 DRAMs, and those run on these higher voltage rails, which is why I have tape on here. I don't want to accidentally put a chip in there because that would absolutely kill it immediately. But this socket right here is for testing these chips here. And I put a little mark there to show me what pin 1 is. So we'll put this in the correct orientation right there, like that. And I don't want to place this down because it would short out on this. So I'll just hold it in my hands. And as it tests, we get lots of blinky blinky happening here. I guess the chip is good, because if the chip were bad, then right away this would fail. Now what this is showing us with these 4 LEDs on this tester is that this is the equivalent of 4 16K RAM chips combined into one, right? That gives us the 64K. And there it is, that chip survives. So the MT RAM being put in the wrong way, well, put in piggybacked the wrong way, still results in a good working chip. We'll put this in there. So this also supports testing 256K RAM chips in here, and the color would be different after the test is done. And that's the equivalent of 4 64K chips. And this socket here for the 16K chips is 4 4K chips, you know, and so on and so forth. So we'll test this one as well. Yeah, you know what? I'm not surprised that these things survived. This is not the first time that I've done this by mistake. And with DRAM, it's pretty resilient and pretty stout. So we'll just pop it on there. That's where I've been holding these chips. We'll let the blinky blinky happen here. So that's a good chip too. So cool. That did not damage those chips. These are some good 4164 chips. Even this terrible MT RAM chip, it's the same 4264 as what's on this motherboard, and yet it still works. So that's it for this video. That's the bonus content. See you later. Bye.